Have you ever stopped to wonder what's really holding you together? I mean, on a microscopic level. Today, we're going to journey deep inside our own cells to meet this incredible team of unsung heroes. These are the molecules that build our bodies, they send out critical messages, and they even fight our battles. They're called complex lipids, and believe me, their secret life is absolutely fascinating. But hey, before we really dive in, I've got a question for you. What do you think builds the walls of every single cell in your body? Now, you might be thinking protein, maybe water, but the real answer is actually one of our lipid heroes. They are literally the foundation of life as we know it. All right, let's meet our first hero. These are the master builders, the actual architects of your entire cellular world. Meet the phospholipids. So what's their secret? How do they build these perfect walls for our cells? Well, it all comes down to this one really powerful property called amphipathic. It's a fancy word, but it just means they have a kind of split personality, a real love-hate relationship with water. And this right here shows that split personality perfectly. See, every single phospholipid has a head that loves water and tails that, well, are terrified of it. So the heads happily face towards the watery environment inside and outside the cell, while the tails desperately try to hide from it. This dynamic actually forces them to line up perfectly, creating the amazing lipid bilayer that forms all your cell membranes. It is structural genius, pure and simple. But get this. Being the master builders is really just the start for them. They are incredibly versatile. They act as a source for cell signals, they anchor important proteins in place, and they even help us breathe by being a key part of lung surfactant. I mean, these guys are the ultimate multitaskers. So, how does our body actually make these essential molecules? Well, you can think of it like a tiny assembly line. You start with a simple backbone, you attach 2 of those fatty acid tails, and then you cap it off with a specific head group. And there you have it, a custom-built glycerophospholipid ready to get to work. Now, within this big family of builders, you also have your specialists, and a really important one is sphingomyelin. This is a unique phospholipid that's absolutely crucial for our nerve tissue. It forms that protective myelin sheath, and it's also a key player in our skin's barrier. A real specialist for some of the most sensitive jobs in the body. Okay, so now we have our city walls built. What's next? We need a security system, right? And this is where our next hero comes in, the glycolipids. These are the key players in our cellular recognition system, helping our cells figure out who's a friend and who's a foe. The best way to think of glycolipids is as molecular ID badges that sit right on the surface of every cell. The carbohydrate part of them sticks out, and it acts as a totally unique identifier that basically tells other cells, hey, this is who I am. And these ID badges they are mission critical. They regulate how our cells talk to each other, they guide how our tissues grow, and, this is a big one, they're how our immune system recognizes self from other, our own cells from some foreign invader. Without them, our cellular world would just be absolute chaos. Okay, so we've got our structures, and we have our security system. But what happens when there's an emergency, like an injury? Well, that's when our third hero has to step in. This is the emergency signal network, run by the eicosanoids, our body's first responders. Right, so unlike our other lipids, eicosanoids are all about action. They are powerful, short-range hormones that act locally, right where they're needed. They're made from a specific fatty acid, arachidonic acid, which gets snipped right out of the cell membrane whenever trouble starts. And their actions? Oh, they're immediate and they are potent. They are the major players in inflammation. They're what cause the pain and swelling you feel. They are absolutely critical for blood clotting, for regulating blood pressure, and for controlling smooth muscle contraction. They're basically the body's emergency alert system. So what's really, really cool is how we can interact with this system. And this brings us to something you've probably wondered about: how aspirin actually works. It is the perfect example of hacking this emergency network. Okay, so let's walk through what happens. First, there's an injury. An enzyme immediately gets to work, releasing that arachidonic acid. Then, this crucial set of enzymes called COX enzymes converts that acid into signals. And the result? Prostaglandins get sent out, causing pain and inflammation, and thromboxanes are released, telling platelets it's time to start clotting. But our body is all about balance, so there's this constant tug-of-war going on. On one side, you have thromboxane A2, which is basically shouting, let's form a clot. And on the other side, you have prostacyclin saying, whoa,
Let's keep the blood flowing. A healthy cardiovascular system really depends on this delicate balance.
And here it is. Here is the aha moment. Aspirin works by physically and irreversibly blocking those COX enzymes. It's like throwing a wrench right into the assembly line. If the COX enzymes are blocked, your body just can't make the prostaglandins that cause pain or the thromboxanes that cause clotting. No COX, no signals. It's that direct. So, we've seen how absolutely essential these lipids are, but what happens when the system breaks down? For our final section, let's take a look at what happens when the builders fail by exploring a group of conditions known as lipid storage diseases. Let's use an example that connects back to our specialist builder, sphingomyelin. Niemann-Pick disease is a devastating genetic disorder, and it's caused by the lack of a single critical enzyme called sphingomyelinase. Its job is to break down old sphingomyelin. Without it, that lipid just builds up and up inside cells, causing massive damage. This table shows just how powerful even a tiny bit of enzyme function can be. In type A, there's a complete deficiency, which leads to rapid neurodegeneration and is, tragically, fatal in early childhood. But look at type B. With just about 5% of normal enzyme activity, it's enough to prevent that severe neurological damage, allowing people to survive into adulthood. It's such a stark reminder of how critical these pathways are. And Niemann-Pick is just one example. It's part of a much larger family of genetic disorders called the sphingolipidoses, which also includes diseases like Tay-Sachs and Gaucher disease. And each one is caused by a single missing enzyme in the breakdown path for a specific lipid, which just highlights how fragile this whole system can be. So let's do a quick recap of our amazing molecular team. We had the phospholipids, our master builders. Then came the glycolipids, the cellular ID badges for recognition and security. And finally, the eicosanoids, the lightning-fast first responders for emergencies like pain and clotting. Together, they keep our bodies running. You know, from building our very bodies to controlling these life and death signals, these lipids are anything but simple fats. They are dynamic, they are essential, and they are incredibly powerful. So the next time you think about your body, remember this. If a single type of lipid can control so much, what other incredible secrets are still locked away inside our cells, just waiting to be discovered?